Yeah, so as Chris mentioned, I'm incoming Associate Director for the Center, but currently I'm still officially with the University of Auckland, New Zealand, as an Associate Professor. So that puts me in a bit of odd position because I haven't worked with the Center, but I still have to explain the work of the Center, but at the same time, I want to also show some of the work we have been doing on the PFAS domain. So I thought this is a unique opportunity to combine the challenges and opportunities, and in the challenge space, I would like to actually showcase some of the work we have been doing in University of Auckland in the PFAS area. And then in the opportunity, I will show the center's projects, current center's projects that address some of the challenges, but that actually are also forward-looking and exciting for me to participate in. So what most of my research has been focused on is aquatic contaminants. And so this is a very basic preliminary slide for any of the environmental chemists. You divide the chemicals into traditional contaminants and then the emerging contaminants. And the emerging space is always evolving, as Lisa pointed out. There are a lot of emerging contaminants getting added, but this is a subjective shading of those contaminants. So the more the yellow, it's more emerging as such, but PFAS is definitely emerging because we know so little of those, and there is so much still unknown to explore. The structure is very generic. Of course, it's not correct for all the compounds. There are always branches and things like that, very weird compounds. But just giving you an overview of CF bond, and can be a chain of the carbon, different chains of the carbon. So I'm not going to talk a lot about PFAS because I think there has been enough introduction given about PFAS. I think a lot of you probably are very well aware of PFAS. But what I would really like to highlight is that people think now that PFAS are getting regulated. So you expect that industries are reducing the release of PFAS in the environment. And that's not the case. So if you look at the figure on your left, it basically shows you how different products are actually contributing to the PFAS release every year. So if you sum it up, it's easily more than 1 million tons per year from different industries. So you can see that, of course, there are consumer products there. Things like ski wax, cosmetics are there. You get the apparels, for example, especially the outdoor apparels and so on. And the paper from Professor Sunderland that showed the exposure pathway shows that whatever ends up in the environment ends up in our body, right? So it's been enough documented. Even previous speakers mentioned how PFAS was found in the baby's tissues and things like that. It's now very well known that PFAS is present in almost everyone's blood, at least in all the industrialized countries. And it's been linked to a number of issues, like high cholesterol levels, decreased vaccine response, and a lot of problems with major organs in the body. And so this is just a brief overview of the guidelines. And to surprise, West Virginia was the first one that came up with the PFAS guideline back in 2002, where they had the guidelines in microgram per liter. And that was mostly driven by their drinking water got impacted by this huge plume of PFAS. And that's why they had to come up with those values. But over the years, EPA has taken control. And now you see the recent guidelines, which have been, again, shown by a couple of speakers earlier, where we are talking about parts per trillion, 4 and 10 parts per trillion. So these 6 PFAS particularly are under EPA's watch. But that list is going to surely grow in the coming years. So I'm going to talk about some of the challenges. And I think Lisa mentioned the challenge about the just limited compounds, less than 100, being currently having standards. So basically what that means is that you can only quantify less than 100 compounds. And there are 15,000 or even more of that. If you apply, for example, OECD definition, there are millions of this PFAS in the environment. And so how do you get the hold of this unknown part? And so Lisa mentioned the total organic oxidizable precursor assay, TOP, and that's a very useful tool for AFFF contaminated sites. But it doesn't work for products. That's what we have been finding out. There is something called total fluorine, which you can get by combustion ion chromatography, which tells you how much fluorine is there in particular product or particular sample you are analyzing. And then you can try to see if you can try to match that fluorine by doing this target analysis with this less than 100 PFAS, or with the top assay where you can actually oxidize everything, try to find carboxylic acid, Or you can do non-target analysis, try to screen compounds which might match some of those things in the library. And if you use that, for some of the AFFF impacted sites, the fluorine balance comes out very close, and so people are very optimistic. People were very optimistic that these tools are enough. But what we are finding out as we know more about it is that if you do that for some of the products, for example, you can't really get those fractions. And that's what I'm going to show in some of the slides, and then why it is eventually linked to our waters. So before that, so apart from those analytical challenges, there are analytical challenges in the lab as well. So as some of you probably know, that polypropylene is recommended for most of the PFAS work in the labs because PFAS sticks to glass. It's been well shown, well demonstrated. So we did carry out this study with polypropylene for some of the short-chain PFAS, and we found that the short-chain PFAS also even stick to this polypropylene. It again depends on the brand. It again depends on which additives have been added to polypropylene. But we see that up to 20% losses can be expected with this polypropylene vials, LCMS vials, pipette tips, and so on. So you have to be careful even analyzing this sample, so proper QA/QC protocol is very much required if you really want to quantify this PFAS accurately. I'm giving the classic example of New Zealand because, first of all, I spent 9 years there. And New Zealand is a unique country in some ways because the government wants to see it as a clean and green. So they have done all their efforts to make sure that tourists are convinced that it's a really clean country, very green country. So they want to be proactive, at least on the surface. They want to do things that shows to the world that we are first. And at the same time, they don't have New Zealand does not have manufacturing industry, PFAS manufacturing industry, particularly. So we thought this would be a very interesting study to look at the concentrations of PFAS in New Zealand and compared to, say, concentrations in US or China, where there's a PFAS manufacturing industry. And so we did this study in different water matrices. I'm just showing the wastewater here. But what we are finding out is that, for example, in wastewater, even if there was no PFAS manufacturing industry, even if PFOA, New Zealand was one of the first ones to ban PFOS and PFOA, you are still seeing PFOS and PFOA in the wastewater. You are seeing the concentrations of short-chain and ultra-short-chain compounds at higher levels. And so we thought like something interesting is going on, mostly because probably it's coming from the products, right? That's been imported. That's the hypothesis. We found also some of the short-chain PFAS in the drinking water, although mostly it came out very clean. But a couple of samples that we detected the PFPRA, the short-chain PFAS in there. So this was interesting, and so that kind of started our focus on the consumer products that are used. Because as I was saying, at least even the wastewater treatment plants in New Zealand are very careful, especially the one we sampled, to not allow any industrial effluent to contribute to their wastewater. So we started looking at some of the products that are available in the market, and the first thing we looked at is cosmetics, because New Zealand EPA actually was very proactive in saying, like, we want to be the first country to ban PFAS in cosmetics, and actually New Zealand is implementing that ban in 12 months. So we took some of the samples from New Zealand and Australia and tested these things for total fluorine. And as you can see, total fluorine content in some of these samples, including mascara, lipstick, so on, came out at screamingly high levels, more than 500 milligram per kilogram. That's a lot of fluorine in there. So we thought, let's do some analysis to understand where this fluorine is. So we did the target analysis, we did the non-target analysis, we did the TOPA, and we couldn't find any of those things here. So all that fluorine is missing, in the sense that it's been in compounds that currently we can't detect, can't analyze. A major challenge for the analytical chemists, because again, companies can come up with some formulations where we have no idea, we don't have the standards, but we can't even detect those with the existing analytical techniques. Then we did something similar with the compostable products that are available in New Zealand market, and we found something very similar. Out of 10 products we tested, majority of the products came out with the higher concentration of total fluorine than their detection limits of 5 milligram per kilogram. One product particularly came up at 810 milligram per kilogram. So again, lots of fluorine in there. But when we did this target, non-target, and TOPA, we could only find one product that came up with concentrations of some of the PFAS, particularly PFOA, which can be a concern. But even still, even if we sum up all that fluorine, it could not account for more than 1%. So what I wanted to highlight through all these things is that the companies are smart, the industry is smart, and actually they have some of those fluorine in the form of fluoropolymers, as well as some of the organic fluorine compounds, which currently we can't, those are not in the library, and we are not able to quantify those. And this is a concern, again, as Lisa mentioned, some of these compounds over the time break down into PFOA, PFAS, and that's what we see in wastewater, right? So those are the challenges, and so I labeled this as a case of missing F based on the clue from the Stranger Things. But what we expect is most of this fluorine is in either fluoropolymers or some of the fluorinated organic compounds, which are not necessarily PFAS, but the possibility, just looking at the literature and so on, is high on the fluoropolymer side. And there's a paper from Rainer Lohmann that came out a couple of years ago explaining the risk of fluoropolymers. So this is something that needs to be monitored even for their breakdown products that may end up in our water and wastewater. So I like to give this analogy of bathtub because this analogy has been given for climate change. And I think that this aptly applies also to PFAS, right? So if you think about the tap as the industry sources of PFAS and the drain as the remediation technologies, you really need to match now that remediation technologies or treatment, the remediation part, to the same way as what we are seeing, like 1 million tons per year release of PFAS from the industry. If we don't match that, the tub is going to overflow, which means that the conditions are going to go out of our hands very soon. And so that's where the opportunities lie. And that's where I thought I will highlight some of the center's current project. I know Yi is going to talk after me, and she's going to go much more in detail with those technical details of those projects. So there are a number of technologies currently available for dealing with PFAS. I grouped those currently into 2 categories. The one is the removal or separation methods. Those can be adsorption membranes, things like that, where they do not destroy, but they separate PFAS from the liquid phase. Or you have a degradation methods like photolysis, or methods like thermolysis with the thermal treatments and so on. And it can be either the single treatment, or you can use a combination of treatments to get rid of the PFAS. And so I'm just coming back to what Chris said about the mission of the center. Our focus is to harness the science, so to engineer the solutions that protect the human health, also environmental health, drive the innovations, and also improve the current water and wastewater treatment technologies. And so what you will see in the next 4 examples I'm showing is that the focus is on trying to improve the current treatment methods with our innovative research. So the first example I'm going to give is the project where the master student, Justice, who is here, he did the work with combining the resins and granular activated carbon in different proportions, in different configurations, try to understand the removal efficiency, optimal removal efficiency of a short chain and a long chain PFAS and their configurations of the column. So this was the kind of setup. The aim was to evaluate the performance of GAC and IX resins columns connected in series for PFAS removal. And as you can see, these were the rapid short columns. So you could actually get this test done in very small amounts of time. But the implications is that the results that you can obtain, you can scale it up and potentially can inform the real world conditions. And so initially, he spiked the 4 PFAS, 2 long chain and 2 short chain. And the information that we get is something like this breakthrough curves. And what it does is it informs us that which combination probably is optimal. As you can see, for most of the PFAS, it's the resins that work really well compared to the granular activated carbon. Currently, the work is undergoing to look at the 6 regulated PFAS that was shown in the previous slides. And also, there is some work going on to transform these results to the real world scenario by testing these columns with the real world groundwater samples. The second example I'm going to give is about the project where the center is working with Professor Ben Shao from chemistry, and we are trying to create novel adsorbents for removal of this PFAS from the water phase. And the focus is on the surface chemistry, so to have the desired functional groups that can actually attract PFAS, bind those, adsorb those, and remove those at a higher rate. And one example here that's been shown here is the cellulose, which is the most abundant biopolymer that's available. And that has been manipulated in the surface chemistry to attach the amine chain, amine alkyl chain, and you can actually distinguish the impact of the electrostatic interactions and hydrophobic interactions by changing the length of the carbon chain and then assessing its impact on the PFAS adsorption. So the results we obtain, something looks like this, and it basically what conveys is that you can actually change the alkyl chain and just understand the impact of the hydrophobic interactions and electrostatic interactions on different PFAS, and those are different. So you can actually get information about how these results can be transferred to the real world conditions and get the knowledge about particular PFAS, which particular PFAS can be removed by which combination of the carbon chains and electrostatic interactions. The next project I'm going to talk about is vacuum UV. And again, Yi is going to go much more in detail about vacuum UV degradation of the PFAS. But it's been shown in the literature that vacuum UV is a very effective way of treating long-chain carboxylic compound, long-chain carboxylic PFAS. Vacuum UV sits at the wavelength less than 220 nanometers, so it's 185 nanometer was the wavelength that's been used in these experiments. It has a high energy photons, which generates for example, aqueous electrons, which can be responsible for degradation of PFAS. So this information has been known, but as you can see on the right side, the PFAS, the sulfonated PFAS, have shown very poor degradation with the vacuum UV. And at the same time, the short-chain carboxylic PFAS have also shown very low removal using vacuum UV. So there is a need to optimize these treatments, and what Yi has been doing is to work in this space to optimize this vacuum UV for the removal of the sulfonated PFAS as well as the short-chain PFAS. And these are some of the optimized conditions she has found. So as you can see, with this optimized condition, the sulfonated PFAS degradation has gone up in the sense that we see very promising degradation of PFAS, for example, with the help of these optimal conditions and the novel device, which he, again, is going to highlight some of these conditions, what she has done. But this is a kind of a novel work in the sense that there is no literature currently about high removal of the PFAS using the vacuum UV, and he is using her research to actually showcase that it is possible. And the last treatment I'm going to highlight, which is again a degradation method, just like a vacuum UV, is the thermal plasma treatment, which we have been doing in collaboration with a physicist from the Stony Brook. And this is the setup, what it looks like. Aim is to develop a small-scale system that will demonstrate the effectiveness of thermal plasma treatment for disintegrating PFAS. And what we have been doing is that using the plasma to see the degradation of P4 and PFAS, the two commonly found PFAS. And as you can see, the initial results look promising. We get up to 50% removal of the PFAS. And the current work is underway to understand the efficiency of this treatment for some other PFAS, but also to improve the existing efficiencies to higher levels and try to understand the reaction mechanisms behind it. So hopefully those 4 projects give you the taste of some of the work going on in the center. And as I mentioned, he is probably going to talk more about these treatments a little bit more in detail in her talk. But what I want to end up the presentation on is some of the future projects that CCWT would be interested to partner in. And those include some of these emerging technologies that are commercially available in the market. And those include something like supercritical water oxidation or electrochemical oxidation, which are more mature in the sense that there has been a pilot-scale treatment system, there has been a pilot-scale demonstration, and as well as there are some systems which are commercially available, as Xiao mentioned. And there are a number of companies that are there in that space, but all these treatment technologies have some limitations. And with the help of the center, what we intend to do is to help these companies overcome some of these limitations, test some of these technologies for their effectiveness of removal of the PFAS, and to showcase that they can actually work in the real world condition. So with that, I would like to hand it over to Yi. Thank you.